Cool. Good morning. Thanks a lot for being here. Thanks a lot for all the lecturers who come partly a long, long way, and for being with us here. And thanks for all the people who contributed to make this possible, and also, of course, to you, the doctoral students, right? The reason we are organizing this this fall school is, of course, that cognition-enabled robot manipulation is the most exciting topic in science, right? And I think I think too few people are working on that, and I think we also need kind of an understanding of the field that goes beyond kind of individual methods, and I think the group of people here, in particular also having some cognitive science background, and from the other side, from machine learning, is a cool group of people to have here. So my purpose for the introductory talk are actually two things. I want to get you an idea of what cognition-enabled robot manipulation is. And I want to remind you of some of the key ideas you should probably already have learned sometime in university. But I think academics has some form of dementia, so that some of the cool ideas and some of the things we already know, they tend to be forgotten, and we make things much more complicated than they possibly are. And I think it's also, I think one of the things that I wanted to get you out of that talk is just some ideas how people kind of think about some problems, right? Also, nobody can really define what cognition-enabled robot manipulation is, right? And because it's kind of a field that is in the beginning, and if we have a science field that is in the beginning, kind of the first thing you are doing, you have to kind of do experiments, right? And when we are doing experiments in something like intelligent agency, so our experiments is actually building systems and trying them out and try to gain insights out of individual experiments. So what we need in order to get the field going is research groups that build complete models for cognition-enabled robotics and run them and study them, right? Only then can we actually look for having a theory for the whole field. So I will take, of course, our system just to present some ideas and just talk about how we set up the problem of cognition-enabled robot manipulation. So for us, the key computation problem is the problem of given an underdetermined manipulation task, something like set the table, bring me something to drink, or anything else, right? What the system has to do, the robot has to generate a body motion, because that's the only thing it can do. It can only kind of, humans can only contract muscles, right? And the robot can only put voltages on motors. So body motion is the only thing that a robot can do. But it has to generate a body motion that, for that under-specified task, achieves the desired effects and avoids the unwanted effects, right? And that's kind of an extremely complex problems. And I think if we are talking about cognition-enabled robotics, there are two other dimensions, right? So one dimension is we do not only want the system to generate the body motion, we also want the system to understand what it's doing. So in a way, you want to ask questions to the system, what are you doing? Why are you doing it? What do you think will happen when you do it? And if you're changing your actions this way, do you think that would work better? And the other dimension is that we want the system to be able to take knowledge, something like advice, and incorporate the advice in its own action, and then do that in a meaningful way. And I think if we kind of have these capabilities together, we are getting a lot closer to what cognition-enabled robot manipulation is. So there's kind of a huge community who set up the problem just as a mapping, right? So you're just taking the object, the task, the environment, and the context. You have some way of a robot that you can observe, and you see behavior and what it's happening. And the idea is, if we just have enough data, enough examples, we can actually learn that function. We can interpolate between the examples, and then we get a system that does all the tasks in the task domain and does it sufficiently. Right? So if you're looking at that, kind of we have a lot of spectacular achievements like winning the Go World Championship, or kind of Watson and what OpenAI does. So there are many examples that are very impressive. But at the same time, we have to be aware that we are nowhere close to the cognitive capability of humans. So even if we are looking at that boy that is not even 2 years old, right? Our systems can't do that, right? And the reason why, the boy is not good in its manipulation capabilities, but it has an understanding of what it's doing, right? So it's knowing that it has to stabilize the pot of water on the glass, and that it has to avoid spilling. And our systems just don't do that. They are not capable yet. And the other thing is, if you're looking at manipulation tasks, if you're looking at a manipulation task such as pouring, there are so many variations of pouring tasks. You can pour pancake mix onto an oven to make a pancake. You can fill at the Oktoberfest a glass of Weiss beer. You can pour water out of a pot in order to keep the sausages inside. You even can neutralize acid or extinguish fire, right? And I think what is amazing is kind of the breadth and the variety of the manipulation tasks that fall in a category like pouring, and also the thing that we kind of have to, that every of this variation needs an own pattern of body motion, right? And they are very distinct. And we have to learn kind of all these variations of pouring tasks over our lifetime. And I think that's kind of an amazing task. So if you're looking at machine learning, so I think we have to be aware of some of the limitation, and that's not a problem, right? So I think data-intensive machine learning is a cool tool set that we have. It's a puzzle piece for kind of finding the kind of the underlying mechanism of intelligence, but it's only part of it, right? And there are some things that kind of machine learning has problems with, right? So for instance, a machine learning-based robot control system could try to vacuum clean spilled red wine from your precious carpet, right? And the reason is that somehow it's in your patterns. And the question is not whether your system would actually do that or not. Kind of the critical thing is that the machine learning-based systems have no have no means of actually testing whether something that is kind of a pattern-driven inference makes actually sense if I execute it. Or another kind of important component of human intelligence is that we can imagine our future actions, right? So we can imagine an action we have never done before. So something like filling a glass of coffee, a cup of coffee at the bottom of the ocean, right? So it's something that that we have no training example for, but still we could ask a human about what do you expect to happen, and we would get reasonable answers, right? So that's kind of another thing. Also, if we are looking at AlphaGo, AlphaGo can compute kind of the best next move in a Go game, right? But this is kind of very limited with respect to human capabilities of playing Go. So a human can play for another one to win, right? We can let somebody win. Or we can basically play a Go game in order to teach somebody how to win. And I think our skills are not only functions, but they are kind of they are large variety. And also other things, I mean, humans interactively learn not only a skill, they learn tasks, and they learn it together with humans so that they actually also have a conceptual framework below it that allows it to do things successfully. Okay, so the bottom line is that even if at the moment everything looks like everything's getting solved and we are just kind of need another, I think we kind of just have seen the tip of the iceberg of what cognition-enabled control and reasoning is. And I think we need huge amounts of research in all different aspects in order to actually make real progress on the hard problems, right? So let me just show you kind of what we are doing in our group, and this is actually, as I said, so the first step in science is doing experiments, building a system that can do that kind of thing, and that's essentially where we are.
Hi, my name is Gaia, and I'm a PhD student at the Institute for AI at the University of Bremen. In this video, the PR2 is performing the household marathon demo of the EASE project. The idea of the demo is that the robot executes different variations of mobile pick and place, whereby it needs to act completely autonomously with the minimal amount of human interference. The first task is to set a table for cereal breakfast for one person. This involves 5 objects: a bowl, a spoon, a cup, some milk, and a box of cereal, which have to be brought to the dining table. Afterwards, the table has to be cleaned up, so the washable objects are placed into the dishwasher, the cereal box is placed back into its storage location, and the milk box is thrown away into the trash, as it's assumed to be empty then. The perception system that we use is called RoboSherlock. It employs an ensemble of experts approach based on the principle of unstructured information management. Importantly, it works in assumption-free scenes, which means, for example, that we don't expect a supporting plane to exist for each object. This is required, for example, for the objects in the dishwasher or in the door of the fridge. The motion control framework that we use is called GISCARD. It does whole body control. For the PR2, this means that we control the arms, the torso, the base, and the head simultaneously. It uses a constraint and optimization-based approach with which we can define multiple goals at the same time. For example, grasp the object while looking at your hand, staying away from the joint limits, and avoiding collisions with the environment. The plan executive that we use is called CRAM. It uses the reactive planning approach, such that the plans concurrently perform the motions and monitor their execution. Simply put, this means that if a failure happens, such as an object slips from the gripper, the robot reacts immediately. The sequence of actions and the failure handling strategies are engineered according to a general model of mobile pick and place, and the parameters of actions are inferred at runtime by querying the knowledge base. There are a lot of challenges that need to be solved in order to master these mobile pick-and-place actions. First, the robot needs to have an enormous amount of knowledge about its environment, the task, its own capabilities, the user preferences, the physics of the world, and common sense rules. Second, the robot needs to be able to execute its actions in a wide range of variations. For table setting, this means that it should be able to get any object from any location in the environment and place it at any other plausible location. The robot also has to deal with the non-determinism and the partial observability of the world, which simply put means that acting in the real world very often leads to failures, and the robot needs to be able to recover from them. And it needs to keep its beliefs about the world in a consistent state, as close to the state of the real world as possible. Finally, in order to reach human-level skill and mastery, the robot needs to be able to improve its performance over time based on collected experience. For more information, please follow the links in the description below.
So this gives just an example of the complexity of the problem we are facing, right? And this is only kind of a category of tasks where we only have pick-and-place actions in the robot, right? And still, it's so complicated, right? And the other thing is, for that control system, we also have the ability to ask the system what is it doing and do it, and also learn from experience. So I want to talk a little bit about how we set up the problem and how we are approaching it, right? And as I said, the key problem is, given underdetermined task requests, find the robot body motion that achieves the desired effects and avoids the other ones, the unwanted ones, right? And the way we are setting up the problem is that we are looking at control systems where the robot is equipped with a generalized action plan, a kind of a pattern, a strategy of how to solve the problem, and a motion plan that in a very detailed manner specifies how the robot has to move, right? And in order to actually go from that very generalized, very abstract action plan into the motion plan, so we do a process that we call contextualization. So that's essentially the context-dependent refinement of these abstract and vague action descriptions into concrete body motions. And the way we want to do that is that we want to use knowledge and reasoning in order to go that way. And I will be a bit more specific, but first let us look at how a generalized action plan looks in our approach, right? So the generalized action plan, that's the only plan that was executed in that video. It's roughly this one, right? So it's fetch and place, and we have two formal parameters, the object and the destination. And the plan consists of two steps, right? And it says that at a location where the object that I need to transport is visible and reachable, I have to perform an action, namely I have to fetch the object. And then at the destination, where I can see the destination and the destination is reachable, I have to perform an action to place the object, right? So what we are doing is we are doing a lot of hand waving. We are not saying kind of how we are doing these things, and these kind of how to do that has to be filled in at execution time. So the idea is that we take that very abstract generalized action plan and we combine it with knowledge, right? We have a knowledge base where we have knowledge chunks, something like cups used for table setting have to be clean and unused. Cups in the cupboards are clean. Cups have to be grasped from the outside. But we also might have kind of knowledge chunks which are very general, something like parameterized motions to avoid unwanted side effects. Spilling is an unwanted side effect. So this is very cool, right? And we know that from AI that this is very cool because these knowledge chunks, they are general and modular, right? They are just kind of true or roughly true, but they are applicable in many, many different contexts. In particular, they are applicable in contexts that the robot doesn't know yet, right? So this is actually the key of dealing with an open world, where we basically want the robot to actually act in a promising way in situations that it hasn't encountered yet. Okay, so then let's look at the second component, the motion plan, right? So motion plan, I think there are lots of studies in cognitive psychology where we actually look at how do people structure their manipulation actions, the motions in there. So what we are doing is we are simply taking one of these models, the Flanagan model of manipulation tasks, and because kind of the cognitive psychologists, they are looking at these problems from an analytic point of view, but not generate the motions, we kind of have to refine it to actually go down into the robot control system and make kind of close the gap to the robot motions. So this is this layer down here. And we have to make explicit the motion parameters, for instance, for reaching. That reaching is dependent on the object to be reached, the arm, and the pose from which the robot starts reaching. So in a way, when we do that kind of task, the capability in the robot control system that we want to have is that it should reason at the motion level. So if the system is pouring water out of a pot with potatoes, right? So the kind of thing that the robot control system should infer is things like, I have to grasp the pot by the handle. I have to hold the pot horizontally. I have to tilt the pot around the axis between the handles. And I have to hold the lid while pouring. So these are constraints on motions, right? But the constraints on the motions, they have semantic reasoning. They have kind of a reason for being there that is actually grounded in the effects we want to achieve and avoid, right? And so actually we need knowledge representation and reasoning to work at that level. Okay, so then let's just look at how that process of contextualization actually works for our thing. So for instance, in the table setting video that we have seen. So we are calling our actions in this way. So we are actually ask the robot to perform an action of type fetch and place with an object that is of the type cup, and the destination is the kitchen table, right? So there are a lot of kind of aspects of the task that need to be achieved, but they are not spelled out, right? So something like the cup has to be clean and unused, right? Or when we say put it on the table, we mean that it should be in an arrangement that we typically have our dinner or breakfast in. And I think this is kind of one of the key things that we need our systems to do to fill in these things that are not spelled out explicitly. So when we get these very vague task requests, so what we are doing is we are just taking our generalized action plan, instantiate it with what we get from the task request, and then we are extending it with all the parameters we need for describing the motion that should execute kind of this task, right? And then it comes down to one inference task that the robot has to accomplish. And this is, it basically has to find all the motion parameters of our low-level motion plans such that the robot succeeds to perform the high-level description of the task with all the desired effects and with kind of avoiding all the unwanted effects. So in practice, right, when you are executing that in our plans, this is kind of more complicated, right, because the robot needs to open the drawer in order to see where the spoon is in order to grasp it successfully. So it's actually composed in many different questions, and they are in a time order that makes the individual steps successfully. But this is actually the most fundamental inference task that a robot has to do in order to accomplish manipulation tasks successfully. So, yeah, so this is the way we are going to approach it. So we have an architecture for doing that. And today I just want to get, and you will learn about different components of that architecture and how to program with them in the course of the week. Today I will just try to get some of the high-level ideas of the plan executive, of the perception executive, of the action executive, and I will talk about the knowledge representation and reasoning part of the system in the next lecture. Okay, so let's start with the plan executive. So I did my PhD at Yale, and I had to be a student assistant for the course Introduction in Computer Science, and where basically computer science was taught according to the famous book Structure and Interpretation of Computer Programs by Sussman, right? So the first thing, so in the first lecture, I've looked it up again, it was the fourth illustration on the blackboard in the lecture room. Kind of, it was that, right? And what the lecturer, Ken Yip, actually was pointing out at, if we are looking at computer programs, right? So everybody has a perception that computer programs specify how the computer has to solve problems, right? But what they were emphasizing in that course, right, that the computer program has another purpose that is equally important, right? And this kind of aspect that is equally important is that we as programmers have an idea of how to solve a certain problem, right? We express that idea in a computer program that has a precise and concrete semantics. And this computer program should communicate the idea on how to solve the problem back to the programmers that work with that program, right? And the reason why that is so important, right, is that ideas can change, right? So our problem, we might find out that we have to solve additional problem. We want to generalize the problem so that we can actually use our idea for more problems. We want to enlarge it and kind of basically satisfying these aspects can be extremely complicated, right? So the real concern if you are studying computer science is how to build large programs that can evolve and can effectively control the complexity of the problem that you want to solve, right? And this is kind of what every computer science student actually was taught in the very first lecture, right? Kind of the thing is, if we are looking at cognition-enabled robot control, I think it's the toughest programming task that we can imagine, right? And if we want to make it simpler for our problems, for our robots to actually accomplish this task, we have to make them easier for us, for the robots, right? So we have to look at that we write the programs in a manner that it's easier for the robot to do self-programming, to understand why something is happening, right? But we are not really working on how do we actually represent robot control programs so that it becomes easier to work with them, right? And the methods, it's also lectured in the very first lectures, is abstraction of control and data, and its composition. So we basically want to have modular components in the programs that we can put together, and if they are put together, then they can solve very complex tasks. And we need to think about what are the interfaces between these different components, right? So I think, so one of the things is to make progress in our field is, at least in some approaches, we have to test whether we can actually apply that to cognition-enabled robot control. Another powerful idea in computer science is that idea of interface layer. Pedro Domingos has, for instance, pushed that, right? And the observation is, if you're looking into fields in computer science, like, for instance, database systems, right? So kind of the problem of building database systems was very complicated when they actually were implementing the database systems as navigation systems on data structure, right? But there was the invention of relational database systems, right, where you kind of abstract away from the way database systems are implemented. You introduce a new interface layer with new concepts, and then kind of the field made rapid progress, right? Because now it was possible to separate the research on application systems from the way kind of database systems were implemented, because we have a strong language at the interface layer, right? The same thing happened for high-level programming languages, right? For design languages, for computer hardware, and something like that. So I think another idea is that we can take over to our field what could be a powerful interface layer for cognition-enabled robot manipulation, and can we provide that? If we have such a language, would that actually make progress? So in our system, so if we are looking at what is happening in a robot control system, what are the things that need to be supported? So robot control program is a concurrent program, right? So there are different processes running. They have to be synchronized. There are things like it's event-driven. So the system should support that there are asynchronously arriving events that we have to react to, and important signals are success and failure. I think we have to think of ways how very kind of diverse subsystems like the robot vision system, the reasoning system, and the motion control system have to talk to each other, and do they have a common language, and can they exchange information? And I think failure handling and recovery are other things. So when you want to bring in that idea of an interface layer, these are some of the concepts that have to be represented in that interface layer in an explicit manner, and they have to be supported, right? And kind of we have control structures for that, but you can, of course, so one of the important concepts is semaphores, right? So you have concurrent processes, and you want to avoid that your robot is actually driving away while grasping an object or while doing some manipulation. The proper way of doing that is that you have a manipulation process, you have a navigation process, and you kind of want to forbid the navigation process to drive away while it's doing some other act. And I think the data structure, I think the main data structure that needs a very proper abstraction in cognition-enabled robot manipulation is the action description, right? The kind of the data structure that describes the action, right? So, and yeah, so you're actually describing your actions, and so if you are looking at going to a kind of a location, and so you want a data structure that describes that location, and that data structure also has to take perception commands and implement them, right? So we will kind of learn about action designators and how that works in the course of this week. Perception executive, just getting some other ideas. So one of the key problems is also that we understand problems before we actually decide on what the solution is. I think, again, that's kind of something that is often forgotten. So if we are looking at perception and the robot control system, so there are different perception tasks that a robot control system has to do, right? So for one thing, the perception system has to answer questions, and it has to answer questions based on the image that the robot captures. And the robot control system needs to know very specific things. So something like, does the object I want to pick up have a handle or not, right? And so kind of one of the tasks is question answering. The second one is belief state. So we want the robot to be aware of the environment, because kind of all the decisions have to be made in a context-dependent way. So if I don't know the context, I can't make smart decisions. And the third thing is perception has to be event-driven, right? The perception system always has to look at whether there are things that we need to do. And yeah, so our perception system has a language to describe these different kinds of tasks. There's also other things like perception goes beyond mapping pixels to answers, right? So we could answer questions of what is the temperature of the fluid inside the bottle, right? And we would apply our experience to that. So there is kind of a lot in pictures that is not reflected in the pixels, but we still know them and can use them for action. So the last thing I want to do is looking at the action component, the action perspective, and I think the big thing that we have to be aware if we are looking at motion control and things is how different the models are that we are using in AI and that we are using in motion control, right? And I think this is kind of shown here. So on the AI side, we have objects. We have kind of states in terms of effects in the world, right? In the motion control area, we only have 6D poses and optimized motion. So in this world, we have to specify the whole task as an objective function or constraint and objective-based function in that mathematical language, right? But that system has, of course, no idea of what it's doing. On the other hand, in AI, we can talk about these things, but we kind of don't have an idea of how to make these things actionable, right? So I think one of the big areas that we need to pay much more attention for is how to bridge that gap between these representations, and can we have actually mechanisms that can optimize motions but still have an idea of what they are doing, and they can reprogram themselves. Okay, so yeah, I conclude here. So yeah, so the only thing that I wanted to bring across is to give you just one example of how a robot control system looks that does cognition-enabled manipulation control, right? So there are many other ways, right? But I think at this point, we need to look at concrete systems. We need to do experiments and look at these systems before we make claims about how cognition-enabled robot control should work in the general case. And the other thing is, I wanted to give you an awareness of how big the problem is, right? How many aspects of the problem there are that we even don't look at, right? And that for many of these partial problems that we have there are already very cool ideas that people have actually discovered, but they are completely forgotten, and we rediscover them, or we make our life very complicated because we forgot them. Okay, so that was it.
So this was a kind of challenge because Michael has a lot of more slides, but I took so much time off his talk, so, so I'm sorry. Okay, so any questions? You have to use a microphone. The benefit for using this microphone is we are recording your questions too, so Michael. So any questions? It was almost like a question. Yeah, okay, here's the microphone.
Can you hear me? Yes. Yeah, okay. So it's really cool to see PR2 doing the kitchen tasks. I know that it's been done in the past with RMR3 and other robots as such. Where do you see other options in the home for using this cognition-enabled robotic manipulation?
I think it's the same kind of problem all over the place, right? And I think another kind of interesting task domains are things where you kind of have more diverse effects, right? Pick and place is only relocating objects without changing their state. But then it's like cutting bread, right? Or cutting, so everything becomes more complicated, and I think it's very interesting to look at manipulation actions that change objects, right? And this is kind of a lot more complicated, but it's the same idea, right? It's cut the salad, cut the bread. In both cases, you have to perform the task in a very different way. And we have the knowledge to actually figure out what is the right way of cutting a bread and do that. our robots have no chance. So what are the computation models that can actually go that way, right?
Okay, thank you.
Further questions?
Thank you for your talk. Is in cognitive robotics, is there any principal way of testing and benchmarking the different tasks that you're trying to solve? In this case, there was a kitchen, and but is there any other way of architecting in a principal manner situation so that you can communicate your research and replicate it in different parts of other tasks?
Yeah, so I think there's, for one thing, we can actually benchmark in the task domain, right? So we can actually look at the original state, the task, and the final state, or maybe also on the course of action, and define some performance measure that says how well we are doing. I think in cognitive robotics, and I think that's kind of different to other fields, is the other dimension, the question of how much does the robot actually understand of what it's doing, right? And so what we are doing is, there is Bloom taxonomy, so this is kind of how you actually test if you teach a subject area to students. What are the different levels of understanding that you kind of need and have if you can master that understanding? And that is basically the basic knowledge, whether you have understanding, whether you can transfer it, whether you can analyze it and compare. And I think this is kind of another dimension where we have to benchmark cognitive robotics, because I think the very different thing of cognitive robotics is that a cognitive robotic system has to perform over a lifetime, right? And it has to learn. So it's not enough to actually have performance measures on the episodes, right, which are kind of much more modular, but you actually have to benchmark the capability of this cognitive system to become more competent. And I think we have to work on that, and